In this video, we'll discuss the relationship between two alternative geometric interpretations of an orthogonal matrix. These interpretations aren't competing with each other. Rather, they work together, and having both of them at the same time will come in quite handy for us in just a little bit. Now, the two interpretations have to do with either seeing a matrix as a collection of vectors represented by its columns, or seeing it as an object representing a linear transformation. Let's start with the first interpretation, where we see any matrix as a collection of vectors represented by its columns with respect to some basis. But because now we're talking about an orthogonal matrix, the vectors that its columns represent are orthonormal, meaning they're all unit length and form 90-degree angles with each other. So their relative arrangement is exactly the same as it is for the vectors in the Cartesian basis, but their orientation is quite arbitrary. So that's our first interpretation. Very simple. Now let's talk about the second interpretation, where we see it as an object representing a linear transformation with respect to the same basis. Now, because it's a length-preserving transformation, we're limited to rotations and reflections. And we've been talking about this interpretation all along, so there's really hardly anything I can add to it at this point. The interesting question right now is whether there is a relationship between these three vectors, the three vectors represented by the columns of the matrix, and the linear transformation. And the answer is yes, there is a relationship. There's a very close relationship between these vectors and the linear transformation represented by this matrix. And the relationship is this: the linear transformation is precisely the transformation that will take the elements of the basis into these three vectors. So we know that these linear transformations are rotations and reflections, but for simplicity, let's just say rotations. So it's precisely the rotation that will rotate these three vectors into the vectors represented by this matrix. So it's very simple and very straightforward. Now, how do we show that this is true? Well, let's simply apply this transformation to one of these basis elements and see what we get. Now, we're working in component spaces right now, so in order to apply the transformation by multiplication, we need to represent the basis element, let's work with E1, by its components with respect to the same basis. And its components are, of course, 1, 0, 0. Why? Well, we've talked about it many times before. Because to represent a basis element with respect to the basis itself, we need to take 1 of itself and 0 of all the other vectors. So the components of E1 are 1, 0, 0. For E2 we have 0, 1, 0. And for E3 we have 0, 0, 1. But we're working with E1 now, so let's see what happens when we apply this transformation, the transformation represented by Q, to E1 in component space. Well, we have to multiply this matrix by the vector of components, 1, 0, 0. All right, and what's the result of this matrix product? Well, of course, it's the first column of Q. This is a column picker. It will pick out the first column of Q. Precisely the vector represented by the first column of the matrix Q. So yes, E1 is rotated into the first vector, into the vector represented by the first column of Q. Similarly for the second vector, similarly for the third. So indeed, we easily see that this matrix represents the transformation that will take each one of these basis elements into the vectors represented by the matrix Q. And one final question is, what about the inverse linear transformation? How do we represent the linear transformation that will rotate these vectors, represented by the columns of the matrix Q, back into the basis elements? Well, generally speaking, it will be the inverse of this matrix. But because this matrix is orthogonal, its inverse is its transpose. So there you go. Here is the matrix that represents the inverse linear transformation that will rotate, really rotate and reflect, but for simplicity we're just saying rotate, that will rotate the columns of Q and align them with the elements of this basis. So here we go. Here's the matrix that will rotate the basis into the vectors represented by its columns. And here's the matrix that will take you back and will use these interpretations of these matrices when we talk about the eigenvalue decomposition of symmetric matrices, which will happen in just a little bit.